Hi, I'm Daniel and I teach chemistry at the University of Glasgow. This is the first of a series of short videos that I've made looking at NMR spectroscopy from a bit of an inorganic perspective. They're based upon some inorganic NMR workshops that are given in Level 3 at the University of Glasgow. In this first video, I'm going to remind you of some of the basic principles that underpin NMR spectroscopy and get you to start thinking about molecules from a multi-nuclear perspective. Let's start at the beginning. What is NMR spectroscopy? Well, the clue is in the name, or at least in the acronym. NMR stands for nuclear magnetic resonance. So, this is a spectroscopy that probes the different magnetic states of a nucleus. As you know, atomic nuclei have a number of different characteristics. Each different type has its own characteristic mass. Atoms of the same element all have the same nuclear charge. And different types of nuclei may also have their own characteristic magnetic moment. The magnetic moment of a nucleus is characterized by a quantum number. This quantum number is usually given the symbol capital letter I. As with other quantum numbers, the values that are permitted for I are restricted. In this way, I can only take values of 0, 1/2, 1, 3/2, 2, 5/2, 3, 7/2, and so on. Let's have a look at some examples of the magnetic moments of different types of atom. The simplest atom is hydrogen, and the first isotope of hydrogen is 1H. This nucleus has a nuclear spin quantum number of 1/2. If we look at carbon, the first stable isotope of carbon is carbon-12. This has a nuclear spin quantum number of I equal to 0. This means it has no nuclear magnetic moment and is invisible to NMR. The isotope of carbon, carbon-13, has a nuclear spin quantum number of I equal to 1/2, just like the 1H isotope. Moving on, nitrogen exists as two stable isotopes, nitrogen-14 and nitrogen-15. Again, these different nuclei have different nuclear spin moments. We find I equal to 1 and I equal to 1/2 respectively. If the moment is 0, it cannot be studied by NMR. If the moment is not 0, then in principle it can be studied by NMR experiments. However, there are other factors that affect our ability to record an NMR spectrum. The natural abundances of particular isotopes may be prohibitively low. Looking at oxygen. Most oxygen is NMR inactive oxygen-16. Only a very small percentage of oxygen is oxygen-17. That percentage corresponds to one atom in 2,500 oxygen atoms being oxygen-17. Clearly, the number of stable isotopes, their magnetic spin quantum numbers, and their natural abundances are particular to each element. For example, vanadium has one abundant isotope, vanadium-51, and this has a large value for its nuclear magnetic moment quantum number. In addition to relative abundances of different isotopes, different types of nuclei also have different levels of sensitivity to being measured by an NMR experiment. We quantify this as the receptivity of a particular type of nucleus. We define the receptivity as the relative strength of signal compared to the strength of signal from the 1H isotope of hydrogen. So for example, if you were to measure equal amounts of 1H and 13C nuclei under similar conditions, the 13C signals would be 2 × 10⁻⁴ times weaker than those for the protons. So, as well as the value of the spin moment and the abundance, the receptivity can also be really important if we're trying to acquire an NMR spectrum. I want to show you how this plays out in a couple of comparable examples. The first spectrum is a proton spectrum, or a 1H NMR spectrum. It took about 7 minutes to collect. It has a high signal-to-noise ratio, and from the measurement we get peak positions of the peaks, and we can integrate peak areas and get some idea of the number of different types of proton contributing to each peak. By contrast, the second spectrum is a 13C NMR spectrum of a compound with similar concentration. and it took about 30 minutes to collect. It has a much lower signal-to-noise ratio. We measure the peak positions, but the lower abundance of carbon-13 and the lower receptivity of carbon-13 and the much longer spin lattice relaxation rate of carbon-13 all conspire to make it much more difficult to get useful information about the relative sizes of the peaks and to extrapolate numbers of different sorts of carbon in different environments of a particular compound. From a chemistry perspective, we think of an atomic nucleus as being built up from a number of neutrons and protons. Both the proton and the neutron have an intrinsic spin angular momentum, which is just another way to say magnetic moment. That moment, or momentum, is characterized by a value of I equal to 1/2. In nuclei with many protons and neutrons, the total nuclear spin is the sum of the components of the spin angular momentum of all the protons and neutrons. So the value of I in deuterium is 1. In just the same way that we think about electrons in chemistry as being either aligned parallel or anti-parallel, the spin moments of protons and neutrons in the nucleus also align parallel or anti-parallel. So really this is a vector addition, and we can see that for a helium nucleus, which has a moment of I equal to 0, there is a configuration where the individual spin moments cancel out. Although the value of the spin moment for a given nucleus is part of the physics of quantum chromodynamics, which is notoriously difficult to calculate, there are some simple statements about the possible values of I that we can make based upon simple vector addition and confirmed by all observations. All nuclei with even numbers of protons and even numbers of neutrons have 0 spin moment. That is, all spins are paired, anti-parallel in the ground state. If the number of protons plus the number of neutrons is an odd number, then there must be an odd number of nucleons in the nucleus with an unpaired spin, meaning the spin moment will be a half integer value. And if the nucleus contains both an odd number of protons and an odd number of neutrons, then the number of unpaired nucleons in the nucleus will be an even number, and the number of the nucleus spin moment I will be an integer. Most commonly it will be either 1 or 2 or 3 or 4, etc. Very rarely it might be 0. We need to delve a little deeper into the meaning of the quantity I. The value of I really corresponds to the size of the angular momentum vector. It's useful to think of it as being represented by an arrow of length I. We might think of this vector centered on the atomic nucleus and pointing somewhere to the surface of a sphere. As a vector, I may have different components along different axes of a Cartesian coordinate system. However, it is a fundamental tenet of quantum mechanics that we cannot know all of these component values simultaneously. For exactly the same reasons that in quantum mechanics we cannot know both the position and the momentum of a particle to some arbitrary precision, remember the Heisenberg uncertainty principle, we also cannot know both the angle and the angular momentum to some arbitrary precision. In fact, if we know the size of the projection of I on the z-axis, I subscript z, then we cannot know the value of the projection of I on the x-axis or on the y-axis. This constrains the spatial orientation of I. If we know the value of I subscript z, then all we know is the cone on which I must lie. In an applied magnetic field, the field defines the z-axis. I subscript z is quantized and only allowed to take particular values. In chemistry, we define the quantum number m subscript I as being proportional to the value of I subscript z. The rule is that for a given value of quantum number I, the quantum number m subscript I takes values that range from -I to +I, increasing in integer increments. So for example, for a nucleus with I equal to 1/2, there are two possible states, either mi equals +1/2 or mi equals -1/2. That means the moment is either up or down, somewhere on one of these two possible cones, and we do not know the values of the x and y components. There is a clear and strong analogy to the way we treat electrons. With the quantum number s equal to 1/2, the quantum number ms is able to take possible values of plus or minus 1/2, corresponding to up or down spin electrons.
We've covered a bit about the different magnetic quantum states of a nucleus, but what about the spectroscopy part? All spectroscopy involves the absorption or emission of electromagnetic radiation and a corresponding change in a quantum state. In this case, in NMR spectroscopy, it turns out that the energy of a particular magnetic state is dependent upon the applied magnetic field. The energy of the state is proportional to the product of the size of the applied field and the size of the moment aligned with the field. Mathematically, that's a vector product. For a nuclear moment aligned antiparallel with the applied field, the energy of that state increases as a function of field. For a moment applied parallel, it would decrease in energy as a function of applied field. If we look at a spin I equal to 1/2 nucleus with two possible Mi states, one when Mi equals a plus 1/2 and the other where Mi equals minus 1/2, then in the absence of any field, the states are degenerate. They have the same energy. Apply a field and we get a splitting between the levels that is proportional to the size of the applied field B. In most modern NMR spectrometers, the field is about 10 Tesla, which is about 2 million times stronger than the Earth's magnetic field. 2 million times greater than the magnetic field that turns a compass needle. Spectroscopic absorption happens between these two states, and the energy of the photon is in the radio frequency range. Now, modern spectrometers are very sophisticated, and the description that I've given here fits much better with the now old-fashioned setup of a continuous wave spectrometer. Here, absorption occurred when the energy gap matched the energy of the radio frequency. And in these days, it was easier to fix the radio frequency and sweep the field, and this gives us terms like high field and low field that we still use today. For a more modern explanation of current NMR spectrometers, we should talk about the more precession frequencies and free induction decay and pulse sequences, but today I'm going to stick with the older type of description because it's clear and easily understandable. If the excitation energy just depended upon the nature of the nucleus and the size of the applied field, all nuclei of a particular isotope would absorb at the same energy. NMR would not be a useful tool for characterization. Fortunately, there's one little caveat that's very important. If you have a nucleus and you apply a magnetic field B, this is mostly, but not exactly, the field that is experienced by the nucleus. Magnetic fields interact with magnetic moments, whether they be intrinsic to a particle or created by moving particles. Magnetic fields interact with all electrons in a material, slightly perturbing their motion and creating an induced magnetic moment. We can think of the field experienced at a nucleus as being a sum of the applied field and of the contribution from the induced moments due to the electrons. Now, within a molecule, atoms experience different environments and different distributions of electrons. Think of a molecule of methanol. Each hydrogen atom in the methyl group experiences the same electron distribution and the same induced moment and the same local magnetic field. But a hydrogen atom on the hydroxyl group is in a different environment with a slightly different electronic distribution, a slightly different local field, giving an absorption at a slightly different energy. This is the mechanism by which atoms in different environments give us signals in different places in the NMR spectra. We call atoms in the same environment chemically equivalent and atoms in different environments chemically inequivalent. In the NMR spectra, the ordinate axis of the spectra is called the chemical shift. It is a shift in position of the absorption caused by the chemical environment of an atom. There can be another contribution to the local magnetic field experienced by a nucleus in the NMR experiment. Moments of nearby nuclei, aligned with, meaning parallel, or against, meaning antiparallel, an applied magnetic field, will also make a small contribution to the field experienced at the nucleus. The spin orientations of neighbouring magnetic nuclei give rise to the fine structure in the spectra. These are the coupling patterns, and they tell us about the atoms near to the atom that is being probed in the NMR experiment. Let's have a look at a very simple spectra of something that you may have seen before but may not have paid any attention to. Deuterochloroform, CdCl3, is the most widely used solvent in NMR spectroscopy. There are two important reasons for this. Firstly, chloroform is a very good polar organic solvent. It dissolves many types of compound easily. Secondly, normally in solution, the quantity of solvent greatly exceeds the quantity of solute. This isotopically substituted molecule has no protons. So, in a proton NMR experiment, it will be invisible. If we had used normal protonated chloroform, CHCl3, as the solvent, the signals from our compound would have been swamped by the signals from the solvent. However, deuterated chloroform, CdCl3, is not invisible in the carbon-13 NMR spectra. About 1% of all carbon is carbon-13, randomly distributed and very, very difficult and very expensive to remove. So, if you run a carbon-13 NMR spectra of a compound dissolved in deuterated chloroform, the strongest signal will probably come from the solvent. With one carbon atom, CdCl3 gives one peak in the carbon NMR spectra, which comes with a chemical shift of about 77.5 ppm. The chemical shift scale is relative to a standard compound, tetramethylsilane, or TMS for short. This reference compound gives us a single peak for carbon, and we set that to be at a chemical shift of 0. The value of the chemical shift for deuterated chloroform is a reflection of the chemical environment of the carbon atom in chloroform compared to the carbon atom in the reference compound tetramethylsilane. The next feature that requires explanation is that the signal is split into 3 equally intense lines. We can call this a triplet. This fine structure is due to the spin moment of the neighbouring deuterium atom that is directly bonded to the atom. The 2H isotope of hydrogen has a nuclear spin of I equal to 1, with Mi states of +1, 0, and -1. In 1/3 of the molecules being measured, the deuterium is in the +1 state and adds to the field. In 1/3 of the molecules, it is in the Mi state equal to 0, with no net contribution to the field. And in the final third, it is in the -1 state, subtracting from the applied field. We say that the coupling of the carbon-13 nucleus to the deuterium gives us a 1-to-1-to-1 triplet. We have now, more or less, covered all that I wanted to remind you about, but there are a couple of general things that I can say about the NMR spectroscopy of inorganic compounds. Firstly, there is fundamentally no difference between the NMR spectroscopy that you learn about for organic chemistry and the NMR of inorganic things. Atoms are atoms, they follow the same laws of physics. Most spectrometers are set up for proton and carbon-13, but also for fluorine-19 and phosphorus-31 studies. And if you're working with fluorine or phosphorus, perhaps you should make use of this. But you should also be aware that there are hundreds of other nuclei that can be studied. And for the most comprehensive understanding of your compound or your system, you really should consider measuring other nuclei when you can. Now, while there's no difference in the science of NMR spectroscopy of organic versus inorganic compounds, because of the greater range of structures and molecular possibilities that there are in inorganic chemistry, there are a number of issues that crop up more often when dealing with inorganic materials. Firstly, paramagnetism. Paramagnetism in organic chemistry is quite rare. It's much more common in compounds containing D or F block elements. Paramagnetic samples can be problematic. The unpaired electrons bring their own large anisotopic contributions to the internal fields, and also provide an additional mechanism for nuclear spin relaxation, which can result in severe line broadening, often to such an extent that you may not see any peaks at all in your spectra. Secondly, the wider range of types of bonding often puts signals outside the normal range. For example, proton NMR is normally run between 0 and 10 ppm, but diamagnetic transition metal hydrides usually have signals between -30 and 0 ppm. You should realise what is normal really depends on what you're working with. Thirdly, any nucleus that has a nuclear spin value of greater than 1/2 also has a nuclear quadrupole moment, and this can cause a number of problems. Most importantly, is that it enhances line broadening and can make it difficult to even record a spectrum. We don't come across this problem much in the NMR of organic material compounds, but there are plenty of spin equal to or greater than 1 nuclei across the periodic table. Now, the last thing to note is that there are some elements that exist with a number of abundant NMR active nuclei, elements such as boron or tungsten or tin. Different isotopes give different spins and different spectra. And when we study a natural sample, the mixture of isotopes can greatly complicate the spectra. So I hope this introduction was useful. I've posted other videos on more specific aspects of NMR spectroscopy, such as the effects of quadrupolar nuclei or how to deal with isotopologues. These provide a bit more detailed information. For now, thanks for watching.